Hi everyone. We're going to learn about the results of experimental study of photoelectric effect today. Laws of photoelectric effect, which were established as a result of experimental study of photoelectric effect, stated that photoelectric effect will not so happen at any frequency. There has to be certain minimum value of frequency called threshold frequency of the light or incident radiation for photoemission to take place. Below this threshold frequency, no photoemission will occur. The second law of the photoelectric effect says that photoemission is an instantaneous process, meaning there is no time lag between the incidence of light and the emission of free electrons. What it means, it's just a spontaneous process. The moment the light strikes, not just any light, but light of a suitable frequency, strikes the metal surface, there will be emission of electrons. So it's almost an instantaneous or a spontaneous process. The next thing we learned that photoelectric current is directly proportional to the intensity of light. The more is the intensity of light, the more will be the photoelectric current. Further, it says the stopping potential does not depend on the intensity of light. On the contrary, it depends on the frequency of incident light. And not just stopping potential, the maximum kinetic energy of the emitted electrons are also dependent linearly on the frequency of incident light. These were the results for the experimental study of photoelectric effect. However, photoelectric effect and wave theory of light, there was some inconsistency between the two. Three main inconsistencies were deciphered, which could not be explained by wave theory. The first inconsistency, as per wave theory, the maximum kinetic energy of the photoelectron should get affected by the intensity. But experiments on photoelectric effect showed that the maximum kinetic energy does not depend on the change in intensity. So, this was the first inconsistency of the wave theory with the experiments. If I try giving you a gist of this, it means that changing the intensity has something to do with energy. Then, if I'm changing the intensity, it means I'm changing the energy, and by conservation of energy, there should have been a change in kinetic energy of the photoelectrons. But the inconsistency is that kinetic energy of the emitted photoelectrons does not change with the intensity of radiation. The second inconsistency, which wave theory could not talk about, was the relation between stopping potential and threshold frequency. It said only increasing the intensity could overcome the stopping potential. Thus came the second inconsistency. The third inconsistency, which wave theory could not explain, was how is it that photoelectric effect is an instantaneous process? On the contrary, the electron which is absorbing the radiation should take in some finite amount of time for the radiation to be absorbed and then the electron to be emitted. But the practical aspect shows that photoelectric effect is almost instantaneous. These three inconsistencies were not explained by the wave theory. Now, Einstein came forth to give explanation to the inconsistencies which could not be removed by wave theory. He proposed certain things. The first thing he proposed was a particle theory of light for the first time. He said that radiations are made of specific and discrete packets of energy called quanta of energy or radiation. Each energy quantum has a value equal to h nu, where h is Planck's constant, nu refers to the frequency of incident light. These specific packets of quantas of energy are known as photons. Mathematically, he developed a record breaking equation known as Einstein's photoelectric equation, which is mathematically expressed as h nu is equal to phi naught, which is the work function, plus k max, which refers to the maximum kinetic energy. This equation he purely developed by virtue of conservation of energy principle, that energy can neither be created nor be destroyed, it can simply be transformed from one form to another. If a radiation of energy h nu strikes a metal surface, the same is absorbed by the metal surface. The electrons having certain work function required will absorb its own work function energy, and the remainder of the two, that is h nu and h nu naught, will be imparted to the electron as its maximum kinetic energy. So what we witness here is that the maximum kinetic energy is the function of incident radiation frequency. The above equation, this entire workout, mathematical, is known as Einstein's photoelectric equation. If we look at it carefully, kinetic energy is the difference of two energies. One is the incident energy, that is h nu. Other is the work function of the metal, that is h nu naught. That is again an energy. That means if h nu is greater than h nu naught, that is the incident radiation has frequency greater than the work function frequency of the metal surface, kinetic energy will be positive. On the contrary, if h nu is equal to h nu naught, that is we are striking the radiation with frequency equal to its own threshold frequency, kinetic energy maximum for the electrons will be 0. That means the electrons may be free to come out of the metal surface but will never come out of the metal surface because they do not have sufficient energy to come out. And finally, if h nu is less than h nu naught, what we witness is kinetic energy will turn out to be negative. The moment kinetic energy is negative, it is not acceptable to us because kinetic energy, we all know, can never be negative. Let's see all the cases. Again, case 1. So what we have here is light of frequency nu, energy h nu, striking a metal surface of work function w naught. There are 3 possible cases. Case 1 says if h nu is less than nu phi naught, that is the work function, energy of the photon is less than work function, no photoemission will occur. If h nu is equal to h phi naught, that is the work function, electron will be able to liberate itself free but will not have enough energy to escape the metal surface because its kinetic energy, I just a while ago said, is 0. If and only if thus h nu is greater than the work function, the energy of the photon will be greater than the work function, electrons will have sufficient energy to come out of the metal surface, and this is when photoemission will occur. Look at this diagram. In this picture, this is a metal shown with work function 2 eV, that is 2 electron volts. This is our Einstein's equation, h nu is equal to phi naught plus k max. If I have supposingly a radiation of 1 eV striking the metal surface, you can see 1 eV less than 2 eV means there will be no photoemission. If on the contrary, I increase the energy of the incident radiation to 2.16 eV, now it's greater than the work function, there will be kinetic energy equal to the difference of 2 with which electrons will come out. And finally, in this diagram, if you see, there is energy of radiation 3.5 eV striking the metal surface. By virtue of the difference between the incident radiation and the work function, kinetic energy of 1.5 eV will be available with the emitted electron, thus justifying Einstein's equation. So the Einstein's interpretation says that photoelectric effect, or current rather, is directly proportional to the intensity of radiation. Because in this picture, the intensity of radiation does not only mean energy, it refers to here the number of photons received by a metal surface in a unit area per unit time. So when we say that intensity of radiation increases, it means we are increasing the number of photons. And when the number of photons increases, more number of electrons will be emitted, more will be the photoelectric current. So more is the intensity, more will be the photoelectric current. He further added, for every metal, there exists a certain minimum frequency below which no photoemission is possible. This frequency is called threshold frequency. Stopping potential and maximum kinetic energy does not depend on the intensity, because intensity here is the number of photons in unit area, unit time. And photoelectric effect takes place only when one electron takes one photon or absorbs one photon. Stopping potential and maximum kinetic energy are thus dependent on frequency and not dependent on the intensity. The relation between stopping potential, maximum kinetic energy, and frequency of incident radiation is as shown. We all know, we just read, this is Einstein's equation, which says that maximum kinetic energy with which the electron can be emitted will be h nu minus phi naught. And if we are talking of stopping potential, the name suggests stopping potential means that retarding potential at which none of the photoelectrons emitted can reach the anode, means the potential required to stop the electron in its own path, to retard its motion. Thus, in such a case, the kinetic energy will be vested as the electrostatic potential energy, that is EV naught. Replacing EV naught here, we get EV naught is equal to h nu minus phi naught. On rearranging this, dividing by E, we get V naught is equal to h by E nu plus phi by E. This is rather minus phi naught by E. What we see further, this is an equation of a straight line. That is, if I plot V naught versus frequency, the graph will be a straight line but having a negative intercept. Negative intercept also joining at x-axis. This particular frequency is a frequency below which there cannot be any photoemission and is called threshold frequency. Thus, the photon picture of radiation, according to this, it says that radiation can behave as wave as well as particle under different situations. And while interacting with matter, it behaves like a particle. Energy of a photon is given by E is equal to h nu is equal to hc by lambda. Here, nu is the frequency, lambda is the wavelength, c is the speed of light, h is the Planck's constant. And the momentum of a photon is given by P is equal to h by lambda, where the symbols have their usual meanings. Photons of similar frequencies possess equal energies, equal momentums. They are neutral. In a photon-particle collision, the total energy always remains constant, the total momentum always remains constant, and the total number of photons may or may not be constant. Thus, the photoelectric effect proves the particle nature of radiation, whereas the phenomenon like interference, diffraction, and polarization proves the wave nature of light. Hence, we can say that radiation displays both wave nature as well as particle nature, meaning a radiation possesses wave particle dualism. Thank you.